for giving me the opportunity to present my work. So the title is changed. It's now Phase Transition System of Soft Elliptical Disk on a Lattice. So this work is done with Professor Kabir Ramola at TIFR Hyderabad. And this is still an ongoing work. And I just wanted to present here and get some feedback from the statistical physics community. Okay, so here's the model. So I'm considering a system of elliptical disks with eccentricity E and that are pivoted at center on a triangular lattice, which has a lattice spacing D. The disks are free to rotate about their centers, and each overlap among their adjacent disks, it costs energy U. And it doesn't depend on the extent of overlap. So that's the simplification we have done here. And in this ensemble, I'm fixing the semi-major axis to unity while the eccentricity is varied. And E is equal to 1 limit corresponds to a rod limit, which has been previously studied in 1 dimension in 2 dimensions, where we see geometrical phase transitions in 1D and 2D and order disorder transition in 2D. So the motivation was what happens if you have some objects that has finite area. So for E less than 1, you get some objects where you have, as you can see, there's a finite area, and whether this order disorder transitions and this geometric transition persists or not. So this is the partition function of this model, and this is something looks like Mayer's expansion, where the first product is over all the disks, and the second product over all the pairs of neighboring disks, and theta is takes the value between 0 to pi, and eta one can think of it as an overlap function, where given two sides which has orientation theta and theta x theta y, if it overlap, it gives the contribution 1 minus exponential minus beta u, and it doesn't overlap, it gives the contribution 0. And u tends to 0, infinity limit gives the hardcore limit, where now then this function just becomes a collection of ones and zeros. And for d is equal to 2, from this geometry, as you can see, because we have fixed the semi-major axis to 1, it becomes a trivial non-interacting limit. So from this formulation, as you can see, this problem boils down to finding whether two disks overlap or not. So now, what's this overlap condition? So unlike circular disks, there is no clean form analytical formula whether two ellipses overlap or not. So in the literature, I found this work by Param and Vardhan in 1984, where they actually developed an algorithm to find out whether two ellipsoids overlap or not. So in this work, I have used that algorithm for elliptical disks. And basically what you do is, it reduces to finding a maxima of some contact function, given the orientation and the centers of the two ellipses. And it just becomes a 1D optimization problem. So that will be the major time-taking step in this problem. And again, for E is equal to 1, this algorithm reduces to checking whether two line segments overlap or not. So using this algorithm, I obtained this overlap region for different eccentricities and D, and we checked that for E is equal to 1, this rod limit, it matches well with our previous work. And as you can see, as you're increasing E, decreasing eccentricity, it becomes more asymmetric. And the overlap region is also, it's increasing. So this problem is not exactly solvable in this triangular lattice. So what we want to do some analytical calculations. So the first thing what we can do is using Bethe lattice, and in Bethe lattice we did some calculations. So this is a 6 coordinated Bethe lattice, and it has, because triangular lattice has 3 distinct directions, so it has 3 distinct directions, and one can write down the Z1, Z2, Z3s along these 3 directions, this restricted partition function, and these are a recurrence relation, and you can use it's a recurrence relation, and one can numerically integrate them out to find a fixed point and construct a probability distribution of thetas. So this is that, and this P of theta, where Z is some normalization constant. And using this, one can calculate some 1-point correlation, some 1-point functions. So next what we did was this nematic order parameter to see whether is a transition or not if you have this eccentricity that's less than 1. So this is a nematic order parameter exponential to I2 theta. It's well known in the community. So at 0.99, very close to this limit, this is not very surprising that there's gonna be a phase transition from large D, and if it's lattice spacing small, it becomes ordered, and large D, it's disordered. And by varying the softness, actually, one can see that it becomes more sharper. And in this hard limit, I think this is showing a very sharp first order jump. But there is some problem in this numerical implementation of Bethe lattice because there is a convergence issue. So that's why I'm using this soft potentials. So this is not very surprising because this is what we saw in the E is equal to 1 limit. What happened? So what surprising was this Bethe approximation predicts this re-entrant phase transitions. So at large, it disordered and it becomes ordered, and again at smaller, go to smaller limit, it becomes disordered. And by decreasing eccentricity, this region where this transition occurs, it shifts towards the larger lattice spacing. And that's not surprising because if you're decreasing eccentricity, the area of this disk becomes more. So that's why it did this. But the surprising part is like what it shows this re-entrant phase transition. So one can do this phase diagram in E and D axis and for different softness. And as you can see, not only there is a phase re-entrant phase transition along D axis, but also E. So if you change E also, you'll see disordered, ordered, and then disordered phase. And one thing one can note that for finite beta mu or finite softness, there is no phase transition after a particular U, particular eccentricity. And by decreasing eccentricity, or if you are going to this hard limit, this you will see there will be transition for any finite E. So this is what Bethe lattice calculation predicted. What next we wanted to see whether how much these are very like how much they are closer to reality and check with Monte Carlo simulations. And this is the Monte Carlo simulation and Bethe lattice result. And as you can see, it is the transitions point it predicts very well. There are fluctuations around here. And as you can see in Monte Carlo simulation also, this prediction is verified that, okay, so there is this re-entrant phase transition. So this is for one eccentricity, and this is second eccentricity works well. So these Monte Carlo simulations are taking a lot of time because of that step, because it's 1D optimization problem. So next, what we wanted to, right now this ongoing work is to understand what is the nature of this transition, what happens here, what are the critical exponents, whether it's a first order transition or a second order transition. So that's right now I'm doing. And yeah, so I have done this, and these are the concluding remarks that we study the soft elliptical disk. And this predicts re-entrant phase transition system. And these are verified by this re-entrance is Monte Carlo simulation. And right now we're investigating this nature of phase transitions. Thank you.
Any questions?
Oh, the lattice spacing. Yes, yeah.
So,
We're varying the lattice spacing.
so is it possible to physically understand like why for two extreme limits like d going to 0 and d very large, like this order parameter was 0?
Yeah, I think one thing is this competition between this energy and entropy. So what's happening is it's a finite area. So what's happening if you're keeping the very close? So energy it's going to be same. Like if it's rotate too much, then the energy is not going. It's remaining constant. So that's why the entropy wins because it was to explore all the phase space. Yeah, I think that's the reason. But I think that's why I said in the hard case, in the hardcore limit, this is not with the case because then it will just become jammed. It's just jammed and then nothing happens, and then if you move it a little, there's order and then disorder. But in somehow in soft cases, and I have checked, it's not overlapping all the way, so it's not touching. So this transition happening, this transition, it's not that all the disks are just touching in the phase space. So there is some region where it doesn't overlap. So where this transition happens. So like in this case, yeah, so this case is trivial, but this transition is non-trivial in a way that it's not all this neighboring disks are all not overlapping at every theta.
So I was thinking from a dimensionality point of view. So typically Bethe lattice are like infinite dimensional, I mean, fractal dimension if you define for them. And then you have a 2D system.
Yeah.
So, I mean, they are pretty different also, like in that sense of like, do you, I mean,
Yeah,
is
it's
there any
like
comment
this
about?
coordination number that I just came out. So this triangle lattice, you have 6 coordination number. So here also I'm just looking at 6 coordinated Bethe lattice. So it's like in mean field also, it's you can put this number. In that sense, you're right.
Okay, with the
It means
coordination number, you ensure that this.
yes, yes. It's 6. So you can do 2 like whatever, but this is like there are 6 neighbors, so that's why I'm taking the 6 coordinated Bethe lattice.
Thanks.
Yeah. So I was just curious, why are you calling it a soft elliptical disk?
Okay, because
Are you likening the deformation potential to be likened to the deformation of the ellipses themselves, or?
no, nothing. So it's a very simple model. It overlaps, then you put this energy cost U. That's it, and it doesn't depend upon the extent of overlap. So,
No, no. My question is like, okay, you're penalizing if two ellipses are
yes,
overlapping,
yes.
but is that penalizing leading to, let's say, deformation of the ellipses themselves?
No, no, no,
No.
nothing.
Okay.
Nothing. No.
Okay. All right.
Sorry, maybe you already said. I mean, first of all, I think NMERS, like hard NMERS, in there's also there's re-entrant transition. Is that right? I mean, for some
Yes, so Kmers, I think.
NMERS with K greater than something,
Yes, yes, yeah.
it's the same kind of transition.
That I have to check. I don't think so, but this is, I think, some. I have to like, yeah, we are investigating what's happening, whether this transition is different from the other transition. Yeah, these two transitions, this and this, whether they are in the same universality class or not. So we don't know yet. Because as you can see here, this configurations, it becomes overlaps. They overlap here, and it becomes disordered. And here there is overlap here also, but it's. Uh, but yeah, I have to. We're just investigating.
If no more question, let's thank the speaker.